Today's class is about testing especially in the context of object-oriented analysis and design. Why do we need to test? First of all, testing is important because it is going to deliver high quality product. After testing, we would have ensured that all the quality standards have been met. Moreover, we can also attain user satisfaction. In fact, a stitch in time saves 9. So therefore, if you're able to find out errors much before the maintenance or much earlier during the development itself, we can ensure that the maintenance effort can be reduced and maintenance cost will also be reduced. Again, by testing, we can ensure that we can get accurate results and results which the user can rely upon. But then testing takes half of the labor, hard work of the complete development, and it is also a meticulous process wherein we use a number of procedures, methodologies and methods, and we focus on different aspects while testing a software product. Now, as far as the testing objectives are concerned, the main objective of testing is to find out the error. Ironically enough, it is not to prove the program correctness, but then to find out the errors in the program. We also need to check if the system meets user requirements and whether it is able to successfully execute in the planned environment or not, whether it meets the purpose or not, and whether it does what for what it has been designed. Testing a product is independent of development method, essentially, and object-oriented approach, though it can give rise to special better considerations in the fact that the object-oriented systems have well-defined interfaces, etc. But at the same time, it also introduces new problems what with all the object-oriented concepts such as polymorphism, inheritance, and all these new concepts, they give rise to new problems as well. The test activities are divided basically into verification and validation. Verification checks whether the procedure by which we have built the software is correct or not, appropriate or not. Verification, though, does not guarantee that customer will be satisfied with the product that we have built. Validation, on the other hand, checks whether the result really is what the orderer actually wanted. So validation is totally focused upon the user requirements and user specification. So in short, we can just look upon them as verification is whether we are building the system correctly, that is whether the path we have chosen to build the system is appropriate, it is been using all the proper engineering concepts, and whether it is using the quality standards, whether it is following the appropriate procedures, and the level of verification that we are doing, whether it is appropriate or not. At every stage we are just checking whether the system is being built in a proper manner or not. And validation is basically the end result, that is whether we are building the correct system. Many a time we may build a system which has much more functionality than what the user wants, or much less than what the user wants, or maybe different from what the user wants. So that does not serve the purpose. So what is important is that we should be able to exactly deliver the system that is required by the user. And that, of course, we get to know from the user requirement specification. So in the major important features of verification is that it checks whether the system is well engineered, whether it is error free, whether it also helps to determine whether the software is qualitatively good or not, and whether but then at the same time, verification process, as we already discussed, does not ensure customer satisfaction, because here the importance is not being given to the requirements, rather it is being given to the path that we have followed in developing the system. Validation, on the other hand, is captured by a thorough requirement analysis where there is ample of user involvement, and there is even communication with the user via tools such as prototypes, etc. This always ensures that the system is useful, because first and the foremost thing is it is relying on the requirement analysis. It is going to check one-to-one each and every requirement, whether it is being met according to the user satisfaction or not. For this purpose, it uses a very strong tool, that is the use case diagram, which is a very unique tool being used by object-oriented systems. So what we see is that validation is anyway in place because we have the requirements in hand and we have the user involvement and we have tools such as prototypes in order to ensure that the requirements are met. But then verification requires more focus, so that is why we shall focus on verification. Other activities, in fact, these can also, we can say, form a part of the verification process. In fact, as we said, that testing is an umbrella activity. Umbrella activity means it encompasses all the phases of the software development, right from the requirements elicitation till the maintenance. When you are talking about requirements elicitation, requirements analysis and design, they do not contain code. They contain some specifications, some project deliverables, some models which have been built. Now these models have also to be tested. And the testing here is not by running the software because the software is not yet ready. At this stage, it can be tested by walkthroughs or by reviews by team which is different from those who have developed the product, by conducting meetings to evaluate the project deliverables at each stage, such as plans, code requirements, specifications, with the help of things like checklists, issue lists, and also meetings, inspection meetings. Code inspections are also possible. Then code inspections are very tough and are quite expensive because it requires a experienced programmer's time. And but then once the code is inspected, the code quality will be much higher, better. The most important aspect of testing is that it should be completed within time and cost. So it is very natural for a testing to always overshoot its whatever allocated resources are. So the cost of test activities normally forms 30% of the development cost, but then sometimes can shoot up to 50% because software is an intangible thing. We do not know where all errors have permeated into the software and how often the faults will come and what kind of faults will come, how long they might take to be fixed. So we cannot ascertain, though we can just draw a rough plan, rough allocation, but then it can shoot up to 50% of the project cost. Testing is a part of the project plan. In fact, it has to be planned much before pre-planned. A test plan is drawn basically. And then as far as the final test activities are concerned, that is at the end of the testing, the final set of test activities, that is called as certification. We coin the term as certification. So once the software product has got the certification, then we say that it is totally completely tested. Now testing of analysis and documents, as we have already discussed during reviews and code inspections, etc. The analysis and design have to be verified only through reviews. Faults should be eliminated as early as possible, as again I would say that a fault which is found out early in the stage will not have its cumulative effect on the other stages, and it is we can ensure that at least the fault does not pass on to each and every stages of the development till the maintenance, where rectifying the fault becomes a very expensive affair. Clean room software engineering basically includes frequent reviews, formal specs, teamworks. They use statistical usage profiles for testing, for incremental development, as well as stepwise refinement. Therefore, these we have already been conducting as a part of the traditional software engineering, and though it is not developed to support object-oriented approach, but it focuses on interfaces and externally visible behavior. Basically, the clean room software engineering ensures that testing focuses on the interfaces and externally visible behavior. An error is a human action. Now, before we go ahead with what is an error and how faults occur and how can a system fail, we need to understand the minute differences between these three things and how one leads to the other. So an error is a human action that results in a software fault, and people naturally, to err is human, so people naturally make errors. They can make a typographical error, they can be misinterpreting a specification or misunderstanding the functionality of a module, or sometimes might be thinking about a synonyms which may not show the same perspective, or cannot be interpreted in the same manner. So similarly, some people make mistakes while coding as well, which we call it as bugs. So all these come under the purview of what we call as an error. It's a human error basically. Now when a human makes an error in the software, then this error can give rise to what we call as faults or defects. Now how do we represent an error basically in a DFT? A data flow, it tells you the error in the data flows. A hierarchy chart, that how these modules are interconnected, maybe a design fault is there, and or a source code, that is the errors generally associated with programming, semantics and syntax errors. And an error may lead to one or more faults. So such errors, they lead to one or more faults. There are two types of faults. We call them as fault of omissions and fault of commission. So when you talk about fault of omissions, so if certain specifications have not been programmed, that means we have omitted a particular specification. So a particular requirement of the user is not met. Similarly, fault of commission, if certain program behavior have not been specified, so that means we have committed an error there, that in the sense that the specification itself did not contain. The first one is fault of omission, is that specification is present but then you have not programmed for it. And the second one refers to the specification itself being incomplete. So defects generally fall into one of these three categories. They can be wrongs, or they can be missing items, or they can be extra. Even extra is something not solicited in the case of software development. Important concepts follow the IEEE standard. So a failure occurs when a program misbehaves. So a failure is basically a statistical property of the system in execution. So when a system is executing, if it comes to a halt or behaves erroneously, that becomes a failure. So failure is a consequence of a set of faults coming together. A fault exists in the program code, and when the code is wrong, the fault can be fixed by changing the code. So a fault may cause a failure. If there is no fault, then the program cannot fail. So error leads to faults, while faults lead to failure. Basically, we can never prove that a program is correct or that it does not fail. We can only say that it contains faults. So a test which uncovers as many faults as possible is considered to be successful. Not one which does not bring out the faults. So an error results in faults, and faults result in failure. But then nowadays an active research is going on in the area of proving a program correctness. So the testing process finds faults. It is in some sense a destructive process, because when we are testing, we always try to destruct the given software to see how it behaves under stress and under different kind of borderline conditions, etc. So basically we are trying to show that something is incorrect in testing. One more thing is that it is not appropriate to test your own construction. So I have constructed the software, and I have designed it, I have coded it, and at the same time I develop an affinity towards the software, and I'm totally tuned to giving it the right inputs, because I know that a wrong output given shall not make it work. So that shows my bias towards my own developed software. So it's very important that somebody else who is not a part of the development should test, because he will look upon the software from a different perspective. It is very expensive to have someone else test. Sometimes what we do is the major parts are given to someone else for a special test department or so during integration or system level testing. Otherwise the unit testing the developer does himself. But then at the same time, even if an independent authority has tested it, they should apprise the developer of the faults so that he can rectify them. Testing is a creative activity and is often viewed as dirty work, because you are trying to violate your own software. To develop an effective test, one must have What is an effective test? Effective test is one which brings out the maximum number of faults. First of all, you need to have a thorough understanding of the system. You need to have a knowledge of various types of testing techniques, and you should also have the skill to apply the techniques. Testers are specially trained to do so on various tools and on the testing techniques and methodologies levels, etc. So they should have that skill to apply these techniques in an effective and efficient manner. So efficient, that is within the time and cost considerations, and effective, that it uncovers as many potential faults as possible. So testing is done best by independent testers. So once the fault is known, it is corrected, the software is retested, and the client, in fact, when you're talking about retesting of a software, the corrected unit is tested again, as well as the client, that is any other unit which uses this particular unit, it is also tested. So the main important thing is that it should introduce fewer faults than number of corrected faults, basically. So on an average, it is learned that one new fault introduced for every third fault corrected, means for every three fault corrections, you tend to introduce one more fault into the software on an average. So basically, in all, the number of faults that we have introduced should be much lesser than the number of faults that we have corrected. Defect avoidance is more powerful than defect removal. See, defect removal is a costly affair in the first place. In the second place, you cannot uncover all the possible defects. So in the first place, if we are able to build the software or engineer the maintenance, etc., in such a manner that we can avoid the defect, so that will be much better compared to let the defect occur and then try to remove it. So we strive for defect avoidance with a well thought out and planned development method in object-oriented software engineering. Now, let us have a look at the testing costs. On the y-axis is quantity, and on the x-axis is the amount of testing. So number of missed bugs is highest. Basically, when the quantity is highest, that is when the testing is not done. That is the number of missed bugs. Then once the system software is under testing, after it reaches an optimal amount of testing, the bugs are reducing. And then the bugs become as we do the testing, continue the testing. Once we have over tested, there are no more bugs in the system. So this is the portion where it is under tested, and this is the over testing. So when the number of bugs are minimum, the amount of testing, with the amount of testing, when we are talking about the cost, that is the cost of testing keeps increasing with time, while the number of bugs will decrease to an optimal amount of testing is the one where the cost curve and the number of bugs, they meet at this particular point. So here it is a moderate number of bugs and the cost of testing is moderate, beyond which the cost can increase, and the number of missed bugs we cannot ascertain, but still it leads to over testing of the product. Testing levels are unit testing, integration testing, system testing, and acceptance testing. What is the unit testing? Basically, it confirms that subsystems are correctly coded and they carry out the intended functionality. So first of all, as soon as the units are developed, they have to be checked for their code, whether it is correct or not, whether it is the outputs given by the code are accurate or not. Or at a time, only a single unit is tested and the developer tests it himself. Unit is individual. Now in the case of object-oriented analysis and design, a unit is typically a subsystem or a class, a block, or a service package. So it can even be that initially it has taken a unit as a class, and then it has taken the unit as a block, and then further the service package. So the most micro scale of testing is called unit testing. It is the smallest level of granularity when you are talking about testing. So tests are done on functions or code modules. So there are two perspectives, that you look upon the structure of the code, or you look upon the functionality that it performs. It requires knowledge of the internal program, design, and code. So it might be using the design document and the code snippets, and it is done by programmers and not by testers. So a developer only tests the unit that he has developed. Objectives of the unit testing are to test the function or unit of code, to test the internal logic, to verify internal design, to test the path and conditions covered, and to test, that means we try to find out the total number of independent paths, and we try to design a test case for each of them, and we try to conduct the tests for the paths, the independent set of paths. Then to test the exception conditions and error handling exception situations also. So these are the objectives when we are talking about unit testing. So when do we do a unit test? After the module is coded directly. So what does it take as an input? Since we are also talking about verification of internal design, it uses internal application design as well as unit test plan. See, internal design is nearest to the code. So that is why it's very important that whenever a bug comes in the code, you might also have to review the internal application design document. The output is eventually a unit test report. Unit test is done by the developer, and the methods normally used by, as I told you, are white box testing techniques, that is structural testing basically. The tools that we use are for debugging, to restructure, code analyzers, path or statement coverage tools. So we have tools, software tools for analyzing code, for restructuring code, for debugging, and for path or statement. Debugging, you already know, in most of the integrated development environments we do have a debugger. So it can restructure it, we can have code analyzers and these. So what is important is that we need to be having a the developer should have a thorough knowledge of the testing methodology and how to use these tools. Like for example, Selenium is there, Rational Robo is there. These are several tools which are used for testing, and many open source tools are also available. Integration testing. Now the second level of testing after the unit testing is the integration testing. Integration testing basically shows how one part interacts with the other, whether it is interacting in the appropriate manner or not. Basically testing of combined parts of an application to determine their functional correctness. So standalone they are working well, but then when combined, that is one application is interfacing with the other, at that point of time during the interfacing, is there any issue or not? That is what we are trying to test as a part of integration testing. The parts can, again the parts is what we define as, that is they can be code modules, they can be individual applications which are interfacing with each other, they can be client server applications also on a network. So all these form a part of integration. Goal is to test the interface among the subsystems, whatever you define as the subsystem. Integration testing verifies that certified units are working together correctly. What is a certified unit? A certified unit is basically the one which we spoke of in unit testing, that is which has already undergone the final test activities and has got a green signal to go ahead, so that it is certified. Integration and unit tests can be performed by the same test cases, because essentially the unit test is the one which tests what happens within a unit, and the same test can also be used, because within the unit only there may be a call to the other unit. So the same test can also be used, like for example a block, though of course the perspective is different. When you are testing the unit, you are just looking at the internal logical structure and the code, etc. But when you are talking about an integration test, we are going to see how a procedure call takes place, or how a interfacing takes place with the other application, whether it is smooth or not, or whether there are any hiccups. So use case is a very strong tool for integration test, and use case is a very strong tool in the whole of object-oriented software engineering. And blocks, service packages, subsystems, and the entire system are tested in the same manner. So a block can call a block, a service package can call a package, a subsystem can interface with another subsystem. So integration of all kinds have to be dealt with when you're talking about the complete software. Groups of subsystems and eventually the entire system, that is of course falls under system testing. Now it is carried out by the developers. Now entire system is viewed as a collection of subsystems and determined during the system and object design itself. You decide upon what are your subsystems. So once they are selected for testing, and integration determines the testing strategy. So integration can be performed in different manner. There are different ways. Basically they can follow different strategy. One is the Big Bang integration, bottom up integration, top down integration, sandwich integration, and variations of the above. Basically when you're talking about Big Bang integration, that means you are trying to integrate the complete software or test the complete software at a time. So just run the software where interfacing with all the applications is taking place. So this is generally not suggested for object oriented programming, though in procedural programming it was this could not be done away with. Big Bang integration, that was because of the lack of well defined interfaces between the various functions or modules to that extent as it is there in the object oriented programming. In object oriented programming, a unit is essentially a block or class which all have very well defined interfaces, whereas in the case of procedural languages or the structured programming techniques, there was just this concept of procedure or function and nested blocks, and there the interfaces are not very well defined. So there Big Bang integration was sometimes inevitable, and that was a very risky thing, because in a Big Bang integration either the system works or it comes to a halt. So we may not be able to afford that. So bottom up integration, top down integration, sandwich is basically a mix of both bottom up and top down, and we have several variations of sandwich testing also. So let us look at each of these testing strategies. For the selection, use the system decomposition from the system design. So how the system design is made, we look at it and accordingly we decide upon the strategy. So continuous testing of an application as and when new functionality is added is called incremental integration testing. So that if we want to run the integration testing in parallel to the unit testing, as and when units are being tested, we can go about integrating each unit one by one in an incremental manner. Applications functionality aspects are also required to be independent, so that we can work on the units separately and then we can start integrating them. So there has to be a concurrency aspect is important, that is parallel. It should be able to support the parallel or independent development. It is done by programmers or testers again, because it's a very technical task. So integration testing's objectives are to technically verify if proper interfacing between modules is there, between subsystems. When do we do it? Once the unit testing is over or they are certified units. Then what is the input? Internal design as well as external design also, because and how an application interfaces with the other is a part of the external design. So we have to see whether we are we are able to do what we have given as a part of the external design or not. And the integration test plan also has to be the guideline basically for integration testing. The output is eventually a integration, whether it is integrating well or not, and what were the obstacles faced, etc., and how we have resolved those. So who are the ones who do the integration testing? That is the developers. The kinds of methods which are used for integration testing are white and black box techniques, and we also do a problem management or configuration management. These are the various methods we use as a part of integration testing. Again, we might be requiring tools such as debuggers, restructures, structuring tools, or code analyzers, etc. Again, we need to have a good knowledge about the testing methodology and effective usage of tools. So types of integration testing. Now let us go to these various types of integration testing. This is a Big Bang approach. unit test A, B, C, D, E, F. There are 6 units here, and we are trying to perform a test which is going to activate all the units at a time to see whether they are integrated well or not. So it's not suggested or advised. Bottom-up testing strategy. In this, the lowest layer of units are first tested individually. Then the next subsystems are tested that call the lowermost ones, that is above the lower ones. So those subsystems they call the lowermost subsystems, and then the second level, the third level subsystems call the second level, and the fourth level call the third level, and so on. So the bottommost subsystems are tested individually first, and then they are being called by the higher level ones. So we can see this is a diagram of bottom-up integration. So this is a layer 1, layer 2 and layer 3. So here what we are doing, bottom up means first E, F, G, they are separately tested. Then E and F are integrated with B, means B, E, F, all the three are tested together, how they call each other and how they interact and how the control goes from B to E and then back to B, or B to F and then back to F, etc. Then similarly we test C. C is not calling any lower level layer 3 module, so therefore we test C, and then test G independently, and then we test D and G together to see how D calls G and how the control goes back. And then further the BEF, C and DG, they are all tested together at the level of A along with A, layer A. So first layer 3 was tested, EFG, then layer 2 was tested, that is BCD, and then A is tested along with the rest of them. What are the pros and cons of bottom-up integration testing? It is bad for functionally decomposed systems. See, functionally decomposed systems are basically they start with the user interface, and based on the functionality you are decompose the complete system. So here the most important subsystem is the user interface, but then because of the bottom-up strategy, the bottommost ones or the service packages are first, the lowermost subsystems are first tested, and the user interface is the last one to be tested. So this is not a very good strategy. So it is useful for integrating the following systems. We can use this bottom-up approach for object-oriented systems, real-time systems, and systems which are having strict performance requirements. So there we need to test the bottommost part very well before we go ahead. Top-down strategy, as the name suggests, we start by testing the topmost layer which controls the subsystem for the user interface, then combine all the subsystems that are called by the tested subsystems and test the resulting collection of subsystems. So from top to bottom, we first go to the user interface part, and then the whichever subsystems they are calling, and then whichever subsystems are being called by these subsystems, and so on till the lowermost level. We do until all the subsystems have been incorporated in the test. So we can have a look at this. The layer 1 consists of A, layer 2 consists of BCD and EFG layer 3. So first we test A, then A, B, C, D, A with BCD. Don't forget that this is integration testing. And then eventually A, B, C, D with EF and G. So this is how the top-down integration takes place. Sandwich testing strategy combines the top-down and bottom-up. Basically the system is comprised of, it is looked upon as comprising of 3 layers. That is, a target layer is the middle layer, a layer above the target, a layer below the target. So testing converges at the target layer. So how do you decide upon the target layer if there are more than 3 layers? So there is a rule of thumb or heuristic that we use, that we try to minimize the number of stubs and drivers. So what is a stub and a driver? Stub is basically a small code which is made, which just accepts a particular control, and then it sends back the control. So basically stubs are used as to replace the lower subsystems before they are built, so that when you are testing a upper subsystem which is calling a lower subsystem, if the lower subsystem is not yet built, we can always write a small stub for it, and just to see whether the call to the stub is taking place appropriately or not. The stub is not totally developed into a full-fledged subsystem, but then it simply mimics the lower subsystem. So similarly, a driver, when you're talking about upper subsystem, the lower subsystems being tested first, then they need to be called by an upper subsystem which is not yet developed. Then in that case we can use a driver program which calls the lower subsystem which has already been developed. So it tries to mimic the functionality of the upper subsystem. So both these stubs and drivers, they have to be written. So that is again some additional effort. What we do is that when there are more than 3 layers, if there are 3 layers, then we can consider the uppermost above the middlemost layer, that is the second layer, as the target layer. But in case we have more than 3 layers, in that case among all the layers we choose middle layers apart from the first and the last. We consider whichever layer uses the minimum number of stubs and drivers, we choose that as the middle layer. So in this we have A, B, C, D, E, F, G. So we test bottom layer tests. What are the bottom layer? E, F and G. So E, F and G are tested. E and F are tested with B, and G is tested with D, and both of them are given to the testing of A. So similarly, top layer test is you're testing A, and we test A, B, C, D, and then we are testing A, B, C, D, E, F, G. So that is how we test the top layer tests, and the bottom layer are tested, and together they are tested. This is a sandwich strategy. Top and bottom layers can be done in parallel, does not test the individual subsystems thoroughly before. That is a problem with this, that top and bottom layer tests can be done in parallel, that's okay, but it does not test the individual subsystems thoroughly before the integration. Because thorough testing of the individual subsystems, once they are done, then we can incrementally integrate them. So this is not being done in this case. So we come for a modified sandwich strategy. Besides that, let us look at the pros and cons of sandwich testing. That therefore, because of the non-thoroughness of the procedure, we go for a modified sandwich testing strategy, in which the middle layer is the one with drivers and stubs, top layer with stubs, and bottom layer with drivers. All these are tested in parallel, because middle layer has drivers and stubs to call it, top layer has stubs, and bottom layer has drivers. In this case, you can observe that we are not using any of these. We test E, F, G in the simple sandwich strategy. E, F, G, E and F are tested with B, and G is tested with D and G, and then they are eventually given here. So there is no thorough testing taking place, but they are being developed in a hurry. But in this case, you can take your own time to develop those. Instead, they are replaced by drivers and stubs. The top layer uses the stubs and the bottom layer uses the drivers. So the testing can be happen in parallel. Top layer accesses the middle layer, top layer replaces drivers, bottom can be accessed by the middle layer and it replaces the stubs. So this is the modified testing strategy. So test E, F and B, they are tested. E, F, B, that is like this, and there is a triple test basically going on, and here there is a D and G are being tested, that is a double test, and double test 2, and there is a double test 1 that is of A and C also. So this double test is going on, and then eventually a triple test is conducted between test B, this 1, 2 and 3, all the 3. So this is the modified testing strategy, that they are being tested independently. This is independent to this is independent to this, they are independently being tested, and then they are going here because they have their own stubs and drivers. System testing, basically the entire system is tested in this. The testing basically at the system level means how the end user interacts with the system, and it is carried out again by developers in the first place. In the second place, an acceptance testing takes place, that is the user acceptance. So in that case, the user is goes through the complete software, running the complete software. Now the goal of the system testing is to ensure that the system meets the requirements. So it is, you can say, it talks about many other aspects such as functional requirements and performance requirements and stress testing, and many other focuses are there which ensure that a thorough system testing takes place. And then we have acceptance testing. It evaluates the system delivered by the developers. It is carried out by the client, and it can involve typical transactions which normally a client uses when he is interacting with the system on a trial basis. Then we demonstrate that the system meets the customer requirements. It is once the customer is satisfied with those requirements, then your system is ready to be used. So therefore implementation and testing in this go hand in hand. Testing activities as far as the system test is concerned, we have this unit test, tested subsystems are provided to the integration test, and further it is functional test is performed on it. Subsystem code is there, subsystem code. Then during the interaction, here as far as unit test is concerned, only code is being considered, and in the case of integration, as you can see, design as well as code, both things are considered. And in the functional test, that is the black box testing, that is we are going according to the requirements of the user. So in that case, the integrated subsystems are taken, and we are trying to check whether the system is meeting the functional requirements of the user or not. For that, we also have to refer to the user manual, and ultimately we get the functioning system. All the tests are done by the developer, that is the initial system testing. And we can also see the global requirements means we are talking about the performance test, functioning system. Now we tune the system according to the performance requirements. The global requirements are taken, where the validated system is given for the user. Once the performance testing is done, it is given to the user for testing, and the client's understanding of requirements is being tested here as a part of the acceptance test. Once the client accepts it, then it is tested at the user environment. Till here it has been tested at the developer's side. Here the environment created for the software is also that of the user environment, where it is eventually has to be installed, and the installation test takes place, and we have now a usable system, that is the system is in use, so according to the user's understanding. So these are the tests by the user. It can be by the user 99% of the time, or if the user leaves it to the developer, it can even be by the developer. So the tests are a part of what we call as the system testing. So system testing can be of functional nature, structural nature, performance testing, acceptance testing, installation testing. So impact of requirements on system testing. If the requirements are very explicit and clear, it becomes easy to test the system. Again, whether the use cases are well built or not, whether they are having the clarity or not, to make the functional testing easy. Then quality of subsystem decomposition will decide upon whether the structure is okay or not. Then quality of non-functional requirements, so performance requirements, how you have laid down the milestones for these performance requirements, the yardsticks or the metrics. This also has a large impact upon the quality of the non-functional requirements. And constraints determines the ease. If there are too many constraints, again performance tests take a lot of time and effort. So system testing's objectives are basically to verify system components, whether they perform the control functions, to perform inter-system test, and that is between if you're having more than one system, to demonstrate that the system performs functionally and operationally according to user specification, to perform appropriate types of tests relating to transaction flow, installation, reliability, etc. And then when do we perform this system testing? It follows the integration testing, as we have seen the levels. then it is a higher level of granularity than the integration testing. So input, when we are talking about the input to this system testing, it is the detailed requirements. First of all, is very important. External application design, we have not much to do with the internal has already been dealt with by unit testing, the integration testing. Now we require the external design to see the structure of the overview structure of the system. So a master test plan and a system test plan, both are important, and the output, that is the system test report, is also. So who does it? The complete development team as well as the users as a team will be doing it. So some aspects are done by the development team, and again the user has to go through the system to see whether it meets his requirements or not. The methods again are problem or configuration management. The tools are recommended set of tools for system testing, and again we need to have a thorough understanding of the testing methodology and the effective usage of the tools. Thank you. That is all as far as this particular lecture is concerned, which is focusing only about what generally testing is all about and what are the levels of the various testing levels. In the following lectures, we'll be talking about the test methodologies and the testing process as well. Thank you.